Okay, it's 10:40. So I've hit the record button, and let's look at some solutions, some answers to the questions here. So if you've had a chance to look at the website, the simulation looks like this. So this is where you can change. So you can change the heights of the pipe. So when you have the same elevation, you can just change the height, and then you can also change the area of the pipe according to what. So you can have a pipe with essentially the same throughout, or you can make the pipe narrower and change the height. So depending on what the workshop instructions are, you can manipulate the simulation. And it's actually just going to give you the answer to verify your calculation. So for example, if you do a run, then it will just give you the pressures, the new pressures P2 and the new speeds at the new section of the pipe after changing some parameters. So it's really just a simulation that will give you the answer that you can use to compare to the calculation that you did to verify if you did the correct calculation. Right, so the first question on continuity equation, filling out this table, we won't fill out all the blanks here. I'll just do one to demonstrate the solution, and then you can do the rest for practice. So we're given the continuity equation A1 V1 is equal to A2 V2. We want to find V2 for these parameters. So we're given the original radius of the pipe, R1, and the original speed in that part of the pipe. And then we are given the new radius. That means we change the cross-sectional area of the pipe, and we want to find V2. So as I've mentioned before the break, we rearrange this equation to find V2. So we have A1 V1 divided by A2. What we are given are the radii and not the areas. So instead of calculating the areas individually, okay, you can expand the definition for area. So let me see here. So A1, just copy that over. A1 V1 is equal to A2 V2. V2 is equal to A1 V1 over A2. Okay. So instead of calculating the areas every time, you can expand the definition for area. So area is equal to pi r squared. Yeah, we can assume the pipe is cylindrical, and therefore its cross-sectional area is a circle whose area is pi r squared. So that will be pi r1 squared for area 1 times V1, and then in area 2 you have pi R2 squared, okay, for area 2. So notice that the pi, you have pi divided by pi, which is essentially 1. So that reduces to R1 squared V1 over R2 squared. That's equal to V2. And that's why but given the radii, you can directly solve for V2 without calculating for the area. So it's just the ratio of the radii squared and multiply that with V1. So let's do the first one in the table. Okay. First one in the table, R1 is 1. So we're just really substituting numbers here. So you have 1 squared. Check the units. They're all in base units. So you're fine with just directly substituting. So R1 is 1. Don't forget there's a square. V1 is 2.5. okay, divided by R2 is 0.5. Don't forget there's a square. Okay. Oh, sorry, that's V2. So V2 in that case will be 10 meters per second. Okay. And if you go to the simulation and you enter the values for R1, V1, and R2, then you should also get 10 meters per second for V2 from the simulation. You won't do that now because of lack of time, but you can do that later. All right. Okay, sounds good. And it's the same trick for all the other rows in the table. So you can just do that as practice later on. Now for the second part, Bernoulli's equation. So the input and output heights are given. So let's say this is Y1 and output height Y2 is given. And then R1 is equal to R2 is equal to 0.5 meters. That means the area, since the radius is the same, the area, cross-sectional area is the same. And V1 is equal to 2.5 meters per second. So how does the output velocity V2 compare or equal to V1? Why does the output velocity V2 equal V1? So essentially you have the pipe the same and you're just changing the elevation without changing the radius. So it's the same area there. Speed there is the same as the speed there. So why? Why is the speed the same even if we change the height? So what influences the speed is the cross-sectional area, right? From continuity equation, A1 V1 is equal to A2 V2. Same A, meaning A1 is equal to A2, means that V1 should be equal to V2. Right? So for example, if A1 is 10 meters squared and A2 is also 10 meters squared, so V1, and say V1 is equal to 2.5 meters. So A1 V1 will be 25 meter cube per second. The only way that A2 V2 is equal to 25 meters per second is if V2 is also equal to 2.5 meters per second. Right? So questions relating to speed will relate to continuity equation. The speed is related to the change in the area, cross-sectional area of the pipe. And it doesn't always have, you don't always have to use Bernoulli's equation. If it's just the speed, that's being asked, and you need to relate that to the area or the radius of the pipe, then that's continuity equation. The time you use Bernoulli's equation is when you're dealing with pressure, because Bernoulli's equation tells you how the pressure will change with speed and height. So the next question here, the input pressure is set to 500,000 pascals. So this will be P1. 500,000 pascals. Okay, and use Bernoulli's equation to predict the output pressure P2. So P2 is what you want. Okay, you can check your prediction using the simulation website. Yeah. So what we're given throughout this problem, we're given y1 is equal to 5 meters. Okay, so I'll just remove the decimal place so it's not so cluttered. And y2 is equal to 2 meters. Right, the speed is the same. So V1 is equal to 2.5 meters per second and V2 is equal to 2.5 meters per second as well. Use Bernoulli's equation explicitly stated there. P1 plus 1/2 rho V1 squared plus rho GH1, okay, is equal to P2 plus 1/2 rho V2 squared plus rho GH2. So this is Bernoulli's equation, the full form of it. Okay, check whether you can simplify it, because if you can simplify this long equation, it makes your life easier. V1 is equal to V2. So V1, this term here, 1/2 rho V1 squared will eventually cancel with 1/2 rho V2 squared. Yeah, and we can clearly see that after we rearrange this equation. So we want to find P2. So we rearrange to isolate P2 because that's what we want to find. So it's this P2 that we want to find. So everything else is being added to P2. So to remove this 1/2 rho V squared and this rho GH, we need to subtract them from the right-hand side to remove, to isolate P2. So you have 1/2 rho V2 squared. Okay, we subtract 1/2 rho V2 squared. Okay, and we also subtract rho GH2. Okay. Notice like we're looking at the terms like they are together because they are being added all together as one. They are being added to P2. And so we subtract the whole thing. We don't need to do division or multiplication or anything. And so that cancels out because you subtract something with itself amounts to nothing, but you also have to do the same subtraction on the left-hand side. One, so you have to do the subtraction 1/2 rho V2 squared and minus rho GH2 or Y. Let me just change the H's with Y so we're consistent with what we're using. Rho G. Right, so here when we rearrange, we can now clearly see the speed is the same. So that means 1/2 rho V1 squared minus 1/2 rho V2 squared will amount to nothing, will be equal to 0, right? Because V1 is equal to V2. And so we simplify Bernoulli's equation, the rearranged one, P1 plus rho G Y1 minus rho G Y2 is equal to P2, right? Okay, we know everything, so we can solve for P2. P2 is equal to P1. So I just flip the equal sign. So it's 500,000 pascals for P1 plus the whole thing in brackets. So it's water flowing. So the density of water, 1,000 kilograms per cubic meter, kilograms per cubic meter times G, 9.8 meters per second squared, gravitational acceleration, times the initial height, which was given to be 5 meters. Okay. So this is rho G Y1, what we just did in the brackets. And then we have to subtract rho G Y2. So minus the whole thing in brackets because we're subtracting the whole thing. It's still water that's flowing. So density is still 1,000 kilograms per cubic meter. And still 9.8 meters per second squared for gravitational acceleration. The new height is 2 meters as given in the problem. So your P2 will be equal to, if you do the calculation, 5 to 9,400 pascals. Okay. So that's the P2. The next problem is, do you get the same? Yeah, so we can already have that as our answer for P2. The follow-up question is, do you get the same result when the fluid is static? Meaning, if you solve for change in pressure, delta P, so this one is the change in pressure, or P2 minus P1. Yeah, the pressure changes when the elevation or the height changes. And in lecture 12, we learned change in pressure is equal to the gauge pressure, rho G change in height, rho G times the change in height. So will you get the same result if you've gone through Bernoulli's equation to find P2 and then find delta P? Will you get the same result as to just using the definition for change of pressure is equal to rho G times the change in height? So let's try to prove that. So we've solved for P2. So the change in pressure, which is P2 minus P1, okay, will be equal to the P2 that we solved, 529,400, minus the original pressure that was given, 50,000 pascals, and you'll get a change of pressure of 29,400 pascals. Okay. So this will be the change of pressure you'll get if you've used Bernoulli's equation to solve for P2 and then got the change in pressure. Now, if you used the definition for gauge pressure, rho times G times the change in height, delta H. Okay. So the density, it's water that's flowing, 1,000 kilograms per cubic meter, times the gravitational acceleration, 9.8, times the change in height. So your height change in height is equal to new height minus the original height, right? So you went from so that's 5 meters and 2 meters. So that's a change of 3 meters. Yeah, for your change in height. You would, if you do the calculation, you would essentially also get 29,400 pascals for your change in pressure. Okay. Yeah, and that's why we said the first case of Bernoulli's equation, where the speed is where the fluid is not flowing when the fluid is static, is the same concept like we learned in lecture 12, where the pressure increases when you go deeper or when the depth increases. Right. Okay, are we happy with the solutions for this so far? Any question about that? Oh, yeah, good. All right, and I guess we'll just wrap up the workshop by looking at this table and just doing one example, one row in this table again. So we're given R1, V1, and then we're given the change in height, H1 minus H2. And we're given the initial pressure and the new radius. So we want to find the new speed and the new pressure. So make your predictions for output pressure and velocity first. So let's do the velocity first, actually speed, just speed. So we don't care about the direction. So let's do the speed first. So whenever you just want to find the new speed, looking at when the radius and therefore the cross-sectional area changes, it's just continuity equation, right? So if you're just being asked for the new speed, check first whether you can use continuity equation before going to the more complicated Bernoulli's equation. So for speed, use continuity equation. And I'll just use the third row as an example here. Right. So for the new speed, V2 will be equal to right, R1 squared V1 over R2 squared. Yeah, that's what we've seen earlier. So we don't have to calculate for the area. It saves us some time because we've already worked out here that A1 divided by A2 is the same as doing R1 squared divided by R2 squared, because the pi disappears and area is pi r squared. Okay, so for the new velocity, you have R1 0.5 squared times V1 2.5 divided by R2 0.5. Oh, no. That's why I didn't do the first row, right? Because the first row will give you the same speed. I was looking at the first row, sorry. So we're doing the third row. We're doing the third row. So R1 is 0.7 squared, V1 is 2.5 meters per second, and R2 is 0.5 squared. Okay. So don't forget the square there. So V2 will be 4.9 meters per second. Yeah, doing the calculation. All right, so we can solve for the new speed without going through Bernoulli's equation. Now for the pressure, you really have to use Bernoulli's equation because it's only Bernoulli's equation that relates how the pressure changes when speed or area or height changes. So for finding P2, this is the Bernoulli's equation. To find P2, rearrange Bernoulli's to isolate P2. And we already did the rearranging. Yeah, we did the rearranging earlier here. So I will not go through the rearranging. We already rearranged Bernoulli's equation to isolate P2. So I'll just write the rearranged equation there. P2 is equal to P1. You can also just see P1 plus 1/2 rho V1 squared plus rho GH1, okay, minus 1/2 rho V2 squared minus rho GH2. Okay. Right? We cannot cancel anything out because nothing's the same, for at least for the third row that we are considering, but we know everything. So we're given R1, we're given V1, we're given H1 minus H2, and we're given P1. Okay, so we're given H1 minus H2. We're not given H1 and H2 individually. But if you notice here, okay, rho GH1 and rho GH2 have a common thing that's going. They're both multiplied to rho G. So if we factor rho G out, we can write Bernoulli's equation as P1 plus 1/2 rho V1 squared. So let me just rearrange the order of these pluses and minuses so that it's easier to see the next step. Okay. So in this line of manipulation, what I did was to rearrange the terms so that I put V1s next to each other, V1 and the speeds, V1 and V2 next to each other, and the heights, or H1 and H2 next to each other, right? Then you can easily see how to factor out rho G from that term. So if we do the factorization, we have P1 plus 1/2 rho V1 squared minus 1/2 rho V2 squared plus, okay, rho G is common to this term. So you have H1 minus H2 times rho G. Right? I factored out rho G because rho G appears on both terms. And rho G is the same for both terms. And you have H1 minus H2 in brackets. If you expand out this factorization, you should be able to recover the expanded form. And that tells you that you did the factorization correctly. Okay. Right. So then you know everything now. So P1 is 50,000. Let me just make sure. 500,000 for P1. We're doing row 3. 500,000 for P1 plus 1/2. Yeah, you can actually also do the same factorization for 1/2 rho V1 and V2 squared, but yeah, we'll just leave it as like that. 1/2 times density of water, 1,000 kilograms per cubic meter, times V1, it's 2.5 squared, okay, minus 1/2 times 1,000 times V2 is 4.9 squared, what we solved earlier. Okay, plus H1 minus H2, that's what's given. H1 minus H2 is 2.5. Yep, H1 minus H2. So it's the whole thing, 2.5 multiplied with 1,000, the density, times 9.8 gravitational acceleration G. Right. So then P2, yeah. Carrying out the calculation in your calculator, you should get P2. All right. Any question about what we did in the workshop or the lecture? Yeah, we don't have time to do this bit of the workshop. The solutions will be up on stream, and maybe I can also record a solution. Well, it depends. We'll see. Maybe I'll just upload maybe I'll just upload the complete workout solution for that part. We'll see how it goes with the recording. I might be able to record, but initially I'll first upload the complete workout solution. And then if I can do a recording, I upload the recording. If not, we have the review workshop on Friday. But it's 10 past 11, so I'm quite conscious of the time. So if you don't have any questions about this workshop or the lecture, I know it was a heavy lecture, and I understand it might take some time to assimilate and consolidate in your minds. But if you do get any questions in the coming days, feel free to email me or ask me in the review workshop. All right. Otherwise, I think we'll end this session.